When I first learned about the atomic structure, life was simple. Electron was orbiting the nucleus, kind of like the planets going around the sun. Everything made sense. But then I entered high school and learned that this is wrong. A better way to think about it is in terms of quantum numbers. And there were a few quantum numbers, they had their own rules, and that led to electrons doing this orbital thing, 3D structures, which had this beautiful shapes. But why do they have these shapes, and what exactly are they? Well, none of that made any intuitive sense until now. See, my goal is always to not just understand things, but to try and rediscover them, because I feel that's the best way to learn something. And that's exactly the ambitious goal of this video. So we're going to start by pretending we don't know anything about quantum numbers or orbitals or their shapes. And just by using intuition, step by step, let's see how much we can rediscover it together. So if you're ready for this, let's begin. Since all of this comes from Schrödinger's equations, let's talk to Schrödinger. And let's start at the very beginning. Schrödinger, what's the problem with this planetary model? It's so simple, so beautiful. What's the problem with that? And Schrödinger says, Mahesh, it's terrible. It doesn't explain anything. For example, we have a charge that is accelerating as it goes around. And according to electromagnetic wave theory, accelerated charges should lose energy. They should radiate light. And so if it was losing energy, it would spiral into the nucleus, and it would, it would crash into the nucleus within a few nanoseconds. So it doesn't explain why the atom is stable. More importantly, it doesn't explain the atomic spectra. For example, if you heat up hydrogen and look at the light that comes out of it and analyze it, you will find that it has very specific frequencies. Why? Why those specific frequencies? It doesn't explain that. It also doesn't explain anything about chemistry. So it's just a terrible model. And I'm like, all right, okay, fine. How do we update this model? Well, Schrödinger reminds us that the biggest problem over here is that we are thinking of electrons as tiny balls. And that's not true. We know that they're quantum particles. They have associated wave function with them. And I'm like, yeah, I understand that. We've talked about that in our previous videos and stuff. We can think of them as a wave. It's a mathematical wave. Nothing is really going up and down. But what's concrete over here is that the square of the amplitude represents the probability of finding the electron at that particular spot. So just from looking at this diagram, we can say that, hey, there's a very high probability of finding the electron somewhere over here, low probability of finding it over here, and almost zero probability of finding it over here. So that kind of makes sense to me. All right. So, okay, Schrödinger, how can we use this and think of a model of the, electron with a proton? So how can we model the hydrogen atom over here? And Schrödinger says, okay, so this means we need to think about a wave that is confined in the 3D space, right? And there's a beautiful, powerful analogy where we have a wave that is confined. And that is the wave confined on a stretched string. And I'm like, I understand that, Schrödinger. We know about the waves on a stretched string. If I have a string that is connected at the ends, and if I just pluck it, it's going to produce standing waves. And the beauty about that is that you can't get any frequency you want. The fundamental frequency is where half the wavelength or half the wave fits this string. The next possible frequency is twice of that, when one full wavelength fits the string. And then you can have 1.5 wavelength fitting the string, even higher frequency, and so on and so forth. So I understand that. That's beautiful. So we can see right in front of your eyes, the first thing is that if you confine a wave, we get discrete frequencies are allowed. No frequencies in between are allowed, because at those frequencies, waves would just destructively interfere and cancel each other. So we get discrete frequencies when you confine waves. Beautiful, right? Now, Schrödinger asks an important question. Mahesh, what about their energies? Can you comment on that? And I'm like, yeah, we can comment on that. See, for the fundamental wave, it's vibrating with the lowest frequency. So it's oscillating very slowly. So it has the lowest energy. It's oscillating much faster, higher energy, higher and higher energy, and so on and so forth. So the energy increases as we go up. And Schrödinger is like, that's great. That's great for physical waves. But what about mathematical waves? Like, for the probability waves that we're talking about. Remember, nothing is oscillating up and down over here. How do we think about energies when it comes to probability waves? I'm like, that's an interesting question. How do we think about energies now? Well, Schrödinger says, here's the thing. Over here, if this was a probability wave, then we get very low amplitudes over here, so less probability of finding the electron, very high probability of finding the electron. So we can kind of see the electron is somewhere over here. Now look at this particular wave. We have a node over here. That means the amplitude is 0 in between. So the probability of finding the electron over here is 0, which means if I were to look at the probability clouds over here, it would look like this. So notice over here, the electrons are much more confined to these two regions compared to over here. And from the uncertainty principle, you know that if you try to confine the electrons, reduce the uncertainty in its position, then its uncertainty in momentum increases. And so because of that, you now end up with higher kinetic energy. So you have higher energy because higher uncertainty momenta gives you higher kinetic energy. That's how, if you have a node in the wave function, that represents a higher energy. So this helps us understand something beautiful. The first excited state, whatever that looks like, we don't know it yet, but the first excited state of the hydrogen should have one node in it, because at higher energy, you get a node. And the same thing continues. Over here, you have two nodes. And so the waves are even more confined. Three nodes, even more confined. And therefore, the momentum uncertainty keeps increasing even more. Kinetic energy keeps increasing. So the key idea we get from just by looking at the standing waves over here is that the more the excited state, more the energy, more the nodes. Okay, Schrödinger, so how can we use all of this to start thinking about the electrons in 3D around the proton? Let's start with the ground state. In the ground state, what do we find? Well, if this was a wave function, mathematical probability wave, then the probability over here is 0. The probability increases to a maximum and then goes back to 0 again. That's what it looks like if it was a confined wave. But where is it confined between? Where is our electron wave confined between? Well, we know that one end could be the nucleus. The other end, well, infinity. We have all of space. So we could say that one end is the proton, the other end is all of space. So as we radially go outwards from the proton all the way towards infinity, the probability should first increase. It should start with 0, close to the nucleus, should increase, reach a maximum, and then decrease. Now, of course, the shape of exactly how the probability increases, where it reaches the maximum, all of that, that's not going to be like this, obviously. For that, we'll require the mathematical rigor, but qualitatively, the pattern remains. The probability should increase, reach a maximum, and then gradually decrease off as we go towards infinity. So let's try to simulate that and see what it looks like. So here's our nucleus. And let's start with very close over here. We're going to use dots to represent probability. So you can kind of imagine if there are 100 dots and if there are 3 dots in a particular region, so we can say the probability is 3 divided by 100, 3% of probability of finding the electron over there. So we can use dots to represent probability. The number of dots is a direct representation of how much probability it is. More dots, more probability. Makes sense? Okay. So very close to the nucleus, the number of dots should be very low. So in my simulation, you probably can't see it, but there are a few dots over here and it turns out to be 11. Now let's go radially outwards. For each radius, let's look at how many dots we should have. So we're right now over here. As I go radially outwards, the number of dots should increase. Okay, so let's look at that. Look at that, that's exactly what's happening. As I go farther and farther away, for different radii, the number of dots increases. And in my simulation, at about this particular radius, it peaks out at 600 dots. This is where you have maximum probability of finding the electrons. And then if I go farther out, the probability should decrease. And so let's see, we are going here. The probability will decrease. You can see the number of dots are decreasing. And eventually it should taper off. It should eventually go to, as I go towards infinity, it should tend to become 0. So now let's look at what will the whole thing look like. Well, it looks like this. Isn't that beautiful? We've just built this from the vibrating string. But I'm sure we have so many questions over here. The first question is, wait a second, we might say, Schrödinger, I thought the probability over here is supposed to be minimum, then reach maximum and then decrease off. But it looks like this is the brightest spot over here. Why do we have so many bright spots at the center itself? Well, Schrödinger says that's a really good question. We'll think about it, okay? If I were to put 8 dots at the center, then the probability is corresponding to that much, right? And if I have, let's say, 41 dots over here, clearly more dots, more probability. But look at the density. Because those 8 dots are confined in a very small space, the density is much higher, so it looks very bright. So Schrödinger says, what matters to us is not the density, how crowded the dots are. What matters is at any given radius, how many total dots are there. That represents the probability. So we shouldn't be worried visually when you see the bright spots. What you have to think about is the number of dots. That's what matters. Another reason why the center appears bright is because, remember, this is a 2D projection of 3 dimension. If something is like this over here, when you look at it from the front, it appears to be at the center. And so that's the reason why this looks very bright. Okay. All right. So that kind of explains what's, visually going on over here. But now comes the main question, Schrödinger, what is this? What am I looking at over here? For that, he says, let's take an analogy. Imagine you have a kid who, goes out in the afternoon and he goes out to play, let's say, and you want to know where exactly your kid is in the afternoon. So you decide to follow him secretly and take a picture at, say, exactly 2 p.m. You want to know exactly where your kid is at 2 p.m. You start taking pictures every single day. So the first day you take a picture and your kid is over here. The next day, exactly at 2 p.m., she's over here, let's say. And then next day she's over here. So you keep taking more and more pics. At first it seems like a little bit random. Later on, as you take more and more pics, you get a beautiful map and you realize, oh, wait a second, your kid is mostly found somewhere in this region. So tomorrow, if you had to predict at 2 p.m. where your kid is going to be, you can say that, hey, you know what? My kid is going to be somewhere in this region, isn't it? This is what orbital is. We call this as an orbital. And I'm like, wait a second. This has nothing to do with orbits. The kid is not orbiting at all. And Schrödinger says, exactly. That's not a really great name. An orbital is kind of like a probability map. You can look at that map and you can kind of predict what are the chances where, you can predict you can predict where it's most likely to find your kid. The same thing is going on over here. This is a probability map. So by looking at this, you can say that, hey, there's a very high chance that my electron is going to be somewhere in this region, somewhere in between, inside this region. I know that if you go very far away, the probability of finding is very low. But that is all that is. It does not say that the electron is orbiting. It doesn't tell you what the electrons are doing. All you can talk about is the probability of finding the electron, and that's the orbital. And again, I'm so happy that we were able to figure this out. Like, we were able to build this out just by looking at the stretch string intuitively. Wouldn't it be so awesome if you could rediscover all concepts like this? Well, guess what? You can, to some extent, using Brilliant, who's sponsoring this video today. Now, I recommend Brilliant to everyone, but you don't have to take my word for it. You can start using it for free by using the link below and start exploring it yourself, and you will see how interactive it is. You learn by doing. And even with a few minutes every day, you can easily become a better problem solver. And what's amazing is that they have courses for physics, math, data, programming, and even AI. For example, I love their calculus course. I mean, just take a look at this. Isn't it so beautiful and so interactive? This actually helps us visualize very complex ideas and helps us actually rediscover these things all by ourselves. And that's, as I said, is the best way of learning things, right? Also, they have a mobile app, so you can learn on the go, which means, again, even with a few minutes, you can level up very easily. So like I said, you can try everything that Brilliant has to offer for free for a full 30 days just by going to brilliant.org/FloatHeadPhysics. The link is also in the description, or you can just scan the QR code. You also get a 20% off on their annual premium subscription if you decide to buy. Not only will it help you become a better problem solver, but you'll also be supporting me. All right, back to the video. So this represents the ground state of the hydrogen atom. What happens now if you were to excite it? Well, let's see. Again, going back to the string analogy, we know that the first excited state should have a node in between. So Schrödinger asks, so Mahesh, if you now think about the probability as you go from here to here, what should happen? Well, I'm like, okay, the probability should start with 0. The probability should increase to a maximum because, negative amplitude doesn't matter. Probability is amplitude squared. So the negative amplitude, positive amplitude doesn't matter. So it starts with 0, goes to a maximum, goes to 0 again, goes to maximum again, and then eventually goes to 0. And again, we can confine this between the nucleus and radially going outwards towards infinity. So again, let's simulate this and see what it looks like. So here's our nucleus. Again, it's very tiny. And right at the nucleus, I should have very low probability. And you might not be able to see this, but in my simulation, there are 10 dots over here. Again, we're going to go farther away radially. As I go radially farther and farther away, look, the probability goes to a maximum. About 409 dots over here. And then as I go farther away, it should reduce. And you can see it reduces, and it goes to 0. This is our node. This is our this is the node that we get over here. All right. Further, if I go outwards, it should again increase to a maximum. All right, here it goes, here it goes, here it goes. And again, this is a qualitative pattern. Okay, we don't know, like we're not able to figure out how much is this maximum compared to this maximum. All of that requires math. Qualitative, not quantitative. Okay, but anyways, we get a maximum over here. And again, as I now go farther away towards infinity, it should slowly taper off. It should slowly go to 0. This is what it would look like, right? Okay, so if we build it out, what is it going to look like? Well, this is what we would get. Isn't that beautiful? Look, now we have a region over here, which is a node, which means the probability of finding the electron over here must be 0. And again, compare this to the ground state. Look, the ground state is much smaller. And for this first excited state, you can see the electrons have much higher energy because they have a node. Because they're more confined, they have much higher energy, and so they can be farther out away from the nucleus. Beautiful, isn't it? So we can build an energy map now. This is the ground state, and this is the first excited state. And you might identify them as s orbitals, spherically symmetric s orbitals. But remember, we're pretending we don't know anything about them. So let's keep the names at the side for now. And at this point, I'm like, Schrödinger, I think I got it. For the next excited state, I should have 2 nodes and so on and so forth, right? And Schrödinger says, Mahesh, hold your horses because things are about to get interesting. Mahesh, over here, the node is a sphere. This is a spherical node. But the question is, could we have other shapes for nodes? And I'm like, yeah, could be. But how do we think about that? Well, here's how. In 1 dimension, a node is just a point. There's no other way to have a node. In 2 dimensions, a point becomes a straight line. In 3 dimensions, that straight line becomes a plane, which means I can have a planar node. And I'm like, okay, how do I visualize this? So he says, let's take our excited state that we just got. Let's get rid of that spherical node. Use a plane to slice this right at the center, and you get a node, a planar node right through the center. And immediately my question is, well, why am I slicing it at the center? Why can't I slice it, for example, over here to get a node over there? And Schrödinger says, Mahesh, you have to respect the symmetry. I mean, Schrödinger equation, the Coulomb's potential over here is symmetric. So you need to cut it in a symmetric way. Think about cutting a cake. You cut it right in between to get 2 halves. The same thing over here. You have to cut it in a symmetric way. And so this is another way to build the orbital for the first excited state. You can have a slice in between. So this means the probability goes to 0 over here. Now, of course, in reality, the probability cannot abruptly go from here to here. So the shape will not be exactly like this. If you actually find what the shape looks like, it goes somewhat like this. And I'm like, oh my God, that is the p orbital. This is why p orbitals have a dumbbell shaped, because at the heart of it, what's going on is we're taking a sphere and we're chopping it to get a planar node. This is where it all comes from. I mean, sure, we couldn't get the exact p orbital, but we understood the skeleton of it, why we have 2 lobes. Oh, that is incredible. Now, at this point, we could ask, well, but wait a second, Schrödinger. Why slice it horizontally? I mean, there are 3 axes, so I could slice it this way. I could also slice it this way. And Schrödinger says, exactly, you can slice in 3 different ways, and that's why you don't get 1 p orbital, you get 2 more. And that's why there are total 4 ways of getting the first excited state. You can have a spherical node, or you can have planar node. Isn't that wonderful? And I'm like, at this point, should be like, okay, are there more ways to slice and dice it? Well, turns out, no. There are no other ways to slice it symmetrically. The key idea is we should do it symmetrically. And I'm like, okay, wait a second. Why can't I slice it diagonally? Well, Schrödinger says diagonal slicing gives you an orbital which can be thought of as a linear combination of of these 3. Think of it as a vector, Mahesh. If you have 3 basis vectors, then any other vector in any other direction can be written as a linear combination of these basis vectors. That's what we write it as I cap, j cap, k cap, and stuff like that, right? So it's the same idea. So these are the 3. So you can think of this as the 3 basis orbitals that we have. And so total, we get 4 orbitals. Wow. Okay, so now let's look at some properties of the nodes over here. Well, over here, the node is spherically symmetric. There is no directional property, right? But here, you can see some kind of a directional property. It's oriented this way. This is oriented this way. This is oriented, this way. Okay, it's a little hard to see it. It's coming out of the screen. You can imagine this way. So it gives you a directional property. So look, the spherical node does not give you any directional property. And so we give a name to this. We call this the radial node. So in the first excited state, you can have one radial node. A radial node because, the node is at the same distance from the center anywhere you go. But another way to set up that node, it gives you a directional property. We call that an angular node. So you can either have the node to be radial or you can have the node to be angular. If you have the angular node, that's where the plane slicing it, that's where you get the 3 p orbitals. Again, let's not use the word p, curse of knowledge. But the earlier one, the ground state, has 0 nodes. And now we can go one step further and we can be a little bit faster. If we go to the next excited state, well, we're going to have 2 nodes. And so as we go radially outwards, we should have 2 nodes over here. And so that is the next excited state with 2 radial nodes. And now again, Schrödinger asks, Mahesh, could there be more ways to build it? Because now we have 2 nodes, things get even more interesting. So let's figure this out together. How else can we have these nodes? Well, we can make both these nodes angular, or we can also make one radial, one angular. Let's try that and let's see what we get. So let's make one radial and one angular. So let's get rid of one of the radial nodes and convert that into an angular node, meaning slice it. And if we slice at the center, we should again get a p orbital, a dumbbell-shaped p orbital, but this time it also has a radial node in between. Isn't this making sense? So I know that I should get 3 of these, definitely possible. And you get these 3 if you have one radial node and one angular node in the second excited state. But the last way which we can set up these orbitals is if both of them are angular. So let's do that. Let's take both these radial nodes and convert it into angular nodes. How do we have 2 angular nodes? Well, slice it with 2 planes, says Schrödinger. But how do we slice it with 2 planes? Well, again, we have to respect the symmetry. So again, think about a cake. If you had to make 2 slices symmetrically, how would we do it? Oh, we would do it this way. We would do it this way. So we'll slice one this way and we'll slice the other like this. And that will give me an orbital with 2 angular nodes. And what do you notice? Again, of course, probability cannot abruptly drop out, so the shape will not be exactly like this, but the shape will turn out to be this way. This is the d orbital. This is why the d orbital has 4 lobes, because there are 2 angular, 2 planar nodes, and that's how we have sliced it. Again, I want to keep the d orbital, the name d orbital to the side, but this makes sense, isn't it? And again, the big question is, how can we orient this? Now, my intuition says, well, just like with the p orbital, dumbbell-shaped orbital, we should be able to orient this in 3 different ways, right? So one way this way, another one like this, probably, depending upon how we slice it. But this is where we actually run out of intuition. It turns out that there are more ways to orient this. Now, again, that's not very straightforward. That's not very intuitive, but it kind of makes sense that if you had one angular node, there are 3 ways to orient it. If you have 2 angular nodes, there are more ways to orient it, right? Now, this is where we run out of intuition, we hit a wall, and this is where we just accept that it turns out that there are other ways to set up these nodes. It's complicated stuff, so it's okay. It turns out that there are 2 extra ways of building this. So in total, we get 5 ways of building this orbital, and that's the reason why the d orbital, we call them, has 5. There are 5 different d orbitals. But what's important for us is because they're all built with 2 angular nodes, and at least it gives us some intuition for why they have these 4 lobes. That is beautiful, if you ask me. And now let's try to rediscover our quantum numbers, okay? So the first question we could ask over here is, how do I identify where my electron is? I need to use numbers to identify that. The first number I can use to identify where my electron is the energy level. I could say that my electron is either in the n equals 1 level, or n equals 2 level, or n equals 3 level. So I need a number to represent which energy level it belongs to, and that is the principal quantum number. And that's why it can take integer values. The first one means ground state, second one means the first excited state, third one means the next excited state, and so on and so forth. But that's not enough. For example, if I know that my electron is in this, first excited state, or n equals 2, how do I know whether it's over here or it's over here? In other words, I need to know the shape of the orbital it belongs to. What decides the shape of the orbital? If you look carefully, you'll notice the number of angular node decides the shape of the orbital. Think about it. If you have 0 angular nodes, then the shape of the orbital is going to be spherically symmetric. We call that the s orbital. S doesn't stand for spherically symmetric. I mean, there's some history behind where these S, P, D, F came from. We had some sharp lines and we had some diffuse lines. That's where the word S, P, D comes from. But let's not worry about that. What's important is that if you have 0 angular nodes, then you have s orbital. If you have 1 angular node, look, we get dumbbell shaped orbital, the same shape. We call that the p orbital. And if you have 2 angular nodes, we get again the same shape, the d orbital, and so on and so forth. The shape of the orbital depends upon the number of angular nodes, and that could be our next quantum number. And that's exactly what azimuthal quantum number is. Azimuthal quantum number is basically telling you how many angular nodes are present in your orbital. And let's look at its values now. For the first one, you can only have 0 because there are 0 nodes. In the second one, you can have either 0 or 1 angular node. In the third one, you can have 0, 1, 2. So look, it runs from 0 to n minus 1. Why is it run to n minus 1? Well, because the first state, n equals 1, represents the ground state. Ground state has 0 nodes. N equals 2 has 1 node, so maximum 1 angular node. N equals 3 has 2 nodes, so maximum 2 angular nodes. And that's why the maximum is n minus 1 nodes. Isn't that making beautiful sense now? Okay. But just knowing this, it's not enough, because if I know the shape of the orbital, I still need to know which orientation it belongs to. And that's why I need another quantum number to represent the orientation for that. And that is the next quantum number, the magnetic quantum number. It tells me which orientation the electron belongs to. And this is where our intuition stopped. Remember, for the p orbital, we could intuitively see why there are 3 orientations because of the 3 axes. But for d orbitals, we couldn't explain why there are 5 orientations. There is some connection between the number of angular nodes and the number of orientations you can have. And there is a hand wavy intuition that we can build. It's not rediscovery, but here's something that helps me. Okay, helps me sleep at night, I could say. All right, so here's a different perspective. Okay, so let me just try to look at this in a slightly different perspective. Consider 1 angular node. Okay, how can you set it up in a spinning sphere? I know, like, looks random, but it makes sense. Okay, one way is to set up that angular node as an equator, like you're slicing it in the equator. Okay, I'm just going to draw a sphere over here, and now let's say you spin it along the z-axis. Okay, you can spin it in 2 ways. You can spin it clockwise, you can spin it counterclockwise. What's happening to the node? The node is spinning like this, and it doesn't look like anything is happening, right? It looks stationary. Whether you spin like this or you spin like that, it looks the same, stationary. We will call this orientation the 0 state. So the ML will be equal to 0. But there's another way to orient this node. Instead of equatorial, we can orient it polar, pole to pole. And again, we can spin it in 2 ways. Now, if we spin it, we actually see one node spinning. We see it going this way. And now clockwise and anti-clockwise, we can differentiate. Clockwise will be this way, anti-clockwise will be this way. And so because we see one node moving around now, we can call this as m equals +1 if it's, say, clockwise. And we can call it -1 if it's anti-clockwise. Any other way you orient that node and you make it spin can be written as a linear combination of these 2. And therefore, we have total 3 different states. So if you have 1 node, we have 3 states. They don't directly map to the shape of the orbitals. You have to combine them and stuff, but let's not worry about it. At least it gives you the number why it runs from -1 to +1. Now let's consider what happens if you have 2 angular nodes. Well, how can we set them up? Well, 2 plane slicing. For the sphere, the way we can do that is, 1, we can have 2 equatorial nodes. And again, it is symmetric, so it's at the same distance from the center. Again, if you make it spin in either ways, the nodes don't appear to be moving at all. So this is the 0 state. Now you can have 1 equatorial and 1 polar. And so we get a +1 and -1 because the pole to pole one will spin like this and spin like that. Or you can have both pole to pole, not exactly pole to pole, longitudinal wise, okay? And now if you spin them, both spin this way or that way. And that's why I get +2 and -2. This is the reason why The magnetic quantum numbers run from minus L to plus L. I agree. This was very hand wavy. It's connected to something called the spherical harmonics, and it really didn't want to get into the details of it. We're running towards the end of the video. Hopefully this gives you some intuition for why if you have 2 angular nodes, there must be 5 orbitals, and you can now figure this out. If you have 3 angular nodes, we should have 7 orbitals. It'll run from minus 3 to plus 3. So this is where the third quantum number comes from. It runs from minus L to plus L. It tells you the shape of the orbital. These 3 are enough for the hydrogen. So just from this, we can now explain everything, all the problems that the earlier model had. First of all, look, the electrons are no longer orbiting. They are forming these stationary waves. So there is no accelerated charges, and therefore they don't have to spiral. They don't lose energy, and therefore they are stable. Secondly, what happens? Why do we get the atomic spectrum? Why do we get the hydrogen spectrum that way? Well, imagine we have hydrogen in the ground state. If it absorbs energy, and let's say jumps to the first excited state over here, when it jumps back, look, it goes from here to here and releases the energy, which is exactly the difference between the 2 states. And that particular energy corresponds to a particular frequency according to E is equal to hf. And I think this is the part that you probably know. We've studied that in Bohr's theory. And again, it could now, next time it gets excited to, let's say, this state, it can either directly jump back to the ground state and give another photon of energy, or it can jump to this state and give another photon of energy. So because there are discrete energy levels, that's why we're getting these transitions. It explains the hydrogen spectrum beautifully. But guess what? It can explain more. To do that, for multi-electron systems like helium and everything else in the periodic table, we need one last quantum number that does not come from the Schrödinger's equations. That comes from Pauli's exclusion principle, which says that 2 electrons cannot have the same quantum numbers. And because you know by now that electrons have 2 kinds of spin, spin up and spin down, that means each orbital has a maximum capacity of 2 electrons. And that gives us the last quantum number. Isn't that amazing? We've discovered quantum numbers, the shape of the orbitals, what the orbitals means, all from this one single idea of standing waves and thinking about nodes. I find that absolutely beautiful. But guess what? Schrödinger says this is just the tip of the iceberg because we just talked about the hydrogen. But now with all of this, we can start talking about other elements. And in fact, we can start answering the most fundamental mystery that I always had in my chemistry course, the octet rule. Why does everything have octet rule? Why do noble gases have octets and all of those things? Why everybody loves to have octet, and why certain elements can even break the octet rule to form bonds? All of that can be understood using these ideas, and that's something that we'll explore in the next video.